Alright, today we're going to focus on differentiability and what makes something differentiable. I've mentioned this previous videos, but we're going to spend more time with it today. So I'm going to make this statement first of all, that all differentiable functions are continuous, but not all continuous functions are differentiable. And that's confusing to people. But before I can really explain that more, I want to talk about what makes something not differentiable. Those places that make something not differentiable are at endpoints, at corners, at cusps, and at asymptotes. So let me kind of go back to the statement of here. If I create a function that has no endpoints, it has no cusp, this is a cusp, it has no corners like an absolute value would, and it has no asymptotes, this is considered differentiable. So this differentiable function, you can see, is continuous everywhere. But I could make a continuous function that is not differentiable everywhere. This is definitely continuous. I never had to lift up my pen or pencil. But if you look, there's spots where it's not differentiable. Those cusp, endpoints, corners. So all those things make it not differentiable. So this is why the statement holds true. All differentiable functions are continuous, you can see that, but not all continuous functions are differentiable. So just because it's continuous doesn't mean it's differentiable, but if it's differentiable, we definitely know it's continuous. So let's go down to this function right here. First of all, it's not continuous, and there's lots of different things going on. I did skip over this accidentally. One other spot where there are not derivatives, if there's something where a vertical tangent line appears, and it's very hard for me to draw, but you might want to look on page 100. I'm trying really hard to draw one that has one. Basically, it's any time that you get a vertical tangent line. So if you had a point here and you drew a tangent line to the curve and you got a straight up and down tangent line, that at that point there would be no derivative at that either. Okay. So down here I can talk about where things are differentiable, where they're not differentiable. There is a lot of non-differentiability occurring down here. So I'm going to write that it's not differentiable at x equals 0, at 1 because there's a cusp, at 0 because it's an endpoint, at 2, at 3, then it's okay until we get to 7, and then 9. All of those points are places where this function is not differentiable. I guess I should also put in here between 2 and 3 because it's not differentiable there because there's nothing occurring. Let's go on to a different function, and what we're going to do is we're going to describe the x values at which it is differentiable. So the easiest way to describe where something is differentiable is to find out where it's not differentiable. So right now I'm noticing that I've got cusp here and here, and so that's at 3 and -3. So I'm going to put differentiable everywhere except when x is 3 and -3. On my next picture, again, I'm asked to describe where is f differentiable. I'm going to look for places where it's not differentiable, and that would be at these asymptotes. So just the vertical asymptotes, so it would be a 2 and -2. So I'll say it's differentiable everywhere except at x equals 2 and -2. On this last example, before I take a quick break, we're going to look at where it is differentiable again. The only place it's not differentiable is where these are disconnected. It's differentiable everywhere else. So we're going to say differentiable everywhere except at x equals 0. And we'll finish up this discussion in the second video. In this particular problem, it asked me to find the derivative from the left and the right, and then we'll use that to help describe whether the function is differentiable at x equals 1. In order to do that, I'm going to go ahead and use the alternate form of derivative because I'm just really curious at what's occurring at 1. So I'm going to take the limit as x approaches 1 from the left, and alternate form of derivative says f of x minus f of 1 all over x minus 1. And I will then plug in my square root of 1 minus x squared minus, when I plug in 1, I get 0 all over x minus 1. That leaves me with the limit as x approaches 1 from the left of the square root of 1 minus x squared over x minus 1. So now what I'm going to be doing is looking at this. This is not going to simplify, so I'm going to look at just putting numbers in like 0.999 and see what happens. So I'm going to pick a really, really small number to put in, like 0.9999, and I'll use my calculator to help me out with this. So I'm going to put in 1 minus 0.999 squared, so I'll put 0.9999 times 0.9999, and I want to take that away from 1, so I'll put, I'll make this negative, and I'll add 1. Underneath my square root, then I have this number, and also I'll hit the square root. So I'll go ahead and write that down on my work here. It's 0.01414. So 0.01414 is what I got on the top. On the bottom, when I put in 0.999, I'm going to go ahead and just do it all at once here. Divided by parenthesis 0.9999 minus 1, end the parenthesis. That gives me 0.0001 on the bottom, negative 0.0001 on the bottom. And then when I divide those two things, I end up getting a really, really large negative number. And the smaller or the closer I would get to 1, the larger and larger this number would get. So I know that the answer to this is negative infinity. So the derivative of this goes to negative infinity. The limit from the right of 1 would be values, so like 1.001. And when I plug those in, those values don't even exist because it's undefined on the top. The square root makes it undefined and not able to be figured out. So the limit from the right does not exist since f is undefined for x greater than 1. Therefore, this is not differentiable at 1. I could have even figured that out back here. That is not differentiable, but I want to go ahead and discuss a 1 from the right. The last problem that I'm going to discuss in this unit is this particular piecewise function, and again I'm asked to find the derivative from the left and from the right. So here I will do the limit, or the derivative from the left and right, which I'm going to use alternate form of derivative. So the limit as x approaches 1 from the left. From the left would be this one right here. So it would be f of x minus f of 1 all over x minus 1. And I'm going to put in that function. F of x is x, so I get x minus, when I plug in 1 to the function, I get 1 all over x minus 1. Well, this cancels, and I'm left with the limit being equal to 1. Now I'm going to look at the limit as x approaches 1 from the right. And again, I'm going to use alternate form of derivative. When I plug in or find what f of x is from the right, it's the x squared. And then when I plug in 1, I get 1 all over x minus 1. So now I'm going to evaluate this limit. This limit factors on the top, and then because it factors on the top, I'm able to cancel with the bottom, and then when I use direct substitution, I get my limit is equal to 2. The statement I can then make is that the one-sided limits are not equal. Therefore, it's not differentiable at x equals 1.